Hello, I'm Nguyet, a PhD student of the University of Auckland. Today, I'm going to talk with you about my paper, Computing Close to Optimal Weighted Sources Path in Practice. I'm going to go through introduction, the method that we propose, the experimental resource. First of all, we present what is the weighted reason problem. As you can see here we have an example of 10 triangles or 10 regions. So let D, E, and V be the sets of non-overlapping region edges, vertices of the region respectively. So given T, E, and V, we have a workspace. Now for each region Ti, so we consider Ti as a triangle, and each Ti so will be assigned a positive unit weight Wi. For 2 points, so B and Q on the same triangle Ti, the weighted length or the cost between B and Q so will be the Euclidean distance between B and Q multiplied by the unit weight of Ti. So for a pair of two vertices, U and V, the weighted reason problem asks for the minimum cost path or the weighted sources path between U and V. For example, as you can see here, the minimum cost path between 0 and 1, so is the blue path here. So for example, here, O1 and here, O2 and here, OK. So we call upon O as a Rosen point. The weighted length of the path between 0 and 1 will be the sum of the weighted lengths of all of the subpaths between two consecutive crossing points of the path. So in general, so we currently don't know this problem is NP-hard or not. There is no non-polynomial or even exponential time algorithm for finding the exact weighted sources path. So the existing algorithm to solve this problem currently are on approximation. Very quickly, we present three existing approaches for this problem. They are exploiting Snail Law using heuristic method and apply the composition ideas where the workspace is divided into a grid of cells or using discrete points placed on the edges of the workspace to create a graph of discrete points. Now for our approach, so currently using Snail Law is believed to be able to compute very close to the optimal one. However, they are considered as impractical solutions because we also target to a very close to optimal path. So we exploit the Snail Law and trying to make our method become practical. So for now, we present our method. First, we present how to find the weighted sources path between U and V, crossing a sequence of K edges. As you can see here, so from E1 to the EK, so the sequence of H, the sequence of edges say S. So and then we will have W is the weight list of S. We consider a path PUV from U to the R1 up to the RK to the V here. So one pretty famous characteristic of the problem is PUV has the minimum weighted length crossing S if and only if at every crossing point Ri on EI, for which Ri is not an endpoint of EI, Ri must satisfy Snail Law. We make it a bit clearer here, Ri here, and this angle alpha I and this one beta I, and Wi minus 1 is the unit weight of this region, and Wi here. So crossing Ri satisfies Snail Law here. So now we have two new definitions, snail rate and snail path. So for snail rate, from a point A1 here on E1, so we apply Snail Law from U crossing E1 at A1, then suppose that the hour rate at A1, so crossing E2 at A2. So and we continue doing that until the last hour rate does not intersect the net edge. Then we have the snail rate PM like this one. So and then for snail path, so snail path BUV here. BUV is a snail path if Snail Law is applied at every Ri, and importantly, every Ri must be on the interior of EI, which is not one of the two endpoints of EI. So if we have two Snail arrays, so BP and PC, BP and PC, so BP and PC, so will never intersect each other. So which means, so the case is in this figure will never happen. Based on that, so let M1 be the midpoint of E1, M1 here. So we create a Snail array PM from U to M1 here. So if here three cases of PM, so if V is plus 1 here on the left side of the last array of PM, for example, and in this situation, the weighted sources path from the U to the V must cross only the H from B1 to M1, from B2 to M2 here, and so on. So this is similar for the right. So we trim the H is 1 to only B1, M1, the H is 2 to only B2, M2, and so on. We keep doing that until the Snail array PM hits V on the edges are trimmed to that the length of all of the edges are less than delta. Delta is a very small number that we define. However, if the weighted sources path from the U to the V hits any endpoint of the edge, any endpoint of the edges, so the process will be stopped immediately. Now we present how we can find the weighted sources path between any two vertices U and V on the whole workspace. We first use a graph called D graph. That is a connection between two vertices in D graph will be created if there exists a Snail path between them, which only crosses the interior of the edges. And the weight of this connection will be the minimum weighted length among all possible Snail paths between two vertices. Now we call F HW as a funnel here and the R here. SO is a sequence of K edges, so from the E1 to the EK, and V here. So we have two nodes here. First, the weighted sources path from the R to the V in a funnel. So need to go around the adjacent edges at R and V, as you can see. So actually we have at most 4 paths here. However, we don't need to calculate all of them. Please see in our paper how we can avoid this. Next, from the funnel F, so we can create two new funnels, one combined with C1 and another one combined with C2 here. However, please see in our paper in which case these two funnels are just only one of them or none of them will need to be created. Now for the main algorithm, first we need to build a D graph for the whole workspace. Then we can use any sources path graph algorithm on the D graph to find the weighted sources path between any pair of vertices. So please see in our paper how to build a D graph in detail. So for all of the stuff here. For the experiments, so we have two scenarios. Now we can only present the scenario 2 where we compare our method with the Steiner-Pond method. First, we briefly present what is the Steiner-Pond method. So with the Steiner-Pond method that we compare, on each edge, we place a number of discrete points, also called Steiner-Ponds, evenly along the length of the edge. Then all of these Steiner-Ponds are connected together to create a graph named GM. Then the registrar is used on GM. For our method, so we set up delta equal to 10 to the minus 5 power. After create the D graph, we also use the registrar to find the weighted sources path between two vertices. So we randomly create 600 test cases from 5 to 30 triangles here. For each test case, so we find the weighted sources path of all pairs of vertices by using our method and the Steiner-Pond method. With Steiner-Pond method, we place from 6 up to 400 discrete points on each edge of the Steiner-Pond method. As we believe, if we place more discrete points on each edge of the Steiner-Pond method, the resource will be closer to the optimal one. So we just want to check up to 400 disk response, so whether our method can do better or not. And yes, our method can return a social path and the standard path method, even with 400 disk response. And the running time of our method is also faster. Thank you for your consideration.